It's finally time to talk about one of the most important concepts in all of calculus, the definite integral. Take our idea of Riemann sums, combine it with the idea of limits, and we can calculate the exact area under a curve. Here's kind of a picture about what's going on. Here's that idea using lots of rectangles to approximate the area under the curve. That area is given by this Riemann sum. This summation of f of x sub I delta x from I equals 1 to n, that's the Riemann sum for these n rectangles. But imagine adding more rectangles and more rectangles, making the width smaller and adding up the rectangles, getting a closer and closer approximation. In fact, if we use like infinite rectangles here, we would get an exact area. And that's the idea. We take the number of rectangles with its limit going to infinity. This is the definition of the definite integral, and this gives us the exact area under the curve of a function. Definite integrals are denoted using that integral sign, but you'll see there's an a and a b attached. That represents the interval we're measuring, the interval a to b that we want to find the area under the curve on. And that's equal to the limit of that Riemann sum. To remind you, delta x is still b minus a over n, and we're going to use x sub I as a plus I delta x. And this is totally groundbreaking. We'll be able to exactly compute areas like this shaded region here. Something I want to point out, that our indefinite integrals gave us a function. These antiderivatives should be functions, typically plus c, but this new idea, the definite integral from a to b, this will always output a number since it represents an area. Here we have the limit of a Riemann sum, a definite integral. We'd like to compute it and say what it represents. We have to pick out some things. Let's first remind ourselves, what does all of this mean? Our definite integral looks like this. The limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. Here delta x is the b minus a over n. This is the width of all of those rectangles. X sub I is given to be a plus I delta x. So we sort of have to eyeball some things here. It sure looks like this outside thing, this 1 over n, should be that delta x, whereas the parentheses all squared, that should be the function, with that inside, the 1 plus I over n, that should be our x sub I, the a plus I delta x. So if this is our guess, that 1 over n equals delta x, and delta x equals b minus a over n, well, they both have an n in the denominator. This should mean that 1 has to be b minus a. We're also guessing that that inside part, 1 plus I over n, this is going to be our x sub I, which is given as a plus I delta x. Now this really matches up with our guess of delta x, if we write this as 1 plus I times 1 over n equals a plus I delta x. Because it sure looks like if we match things up, 1 should be a, 1 over n should be delta x. And we already said 1 over n was going to be delta x. So let's go with this. 1 is a, so this now says 1 equals b minus 1, or that b equals 2. A equals 1, b equals 2. Well, if we have that, what's the function? The outside was 1 over n, that was delta x. The inside, 1 plus I over n, that was x sub I. The only thing we haven't addressed yet is that squared. Well, the x sub I goes into the function. What does it go into? It goes into the squared function. This makes f of x, x squared. Meaning that this definite integral represents the area under the curve, the exact area under the curve from x equals 1 to x equals 2 of the function x squared. Now that we have an idea of what it means, let's compute it. It's going to come down to crunching a bunch of numbers, as well as using some reduction formulas. The limit as n goes to infinity of this sum from I equals 1 to n, and we're going to have to expand this. So we have this 1 over n. This thing, 1 plus I over n squared, means times itself. We're just going to FOIL that out. We're going to distribute that out. 1 times 1 would be 1. We'd have 1 times I over n twice. that would be 2i over n, and then I over n times I over n would be I squared over n squared. Next, let's distribute that 1 over n. We still have the limit as n goes to infinity, and this sum. We should write this all the way through until we actually compute these things. So if we push that 1 over n through these parentheses here, we're just going to bump the power of n by 1 in the denominator. This will be 1 over n times 1. We'll have 2i over n squared plus I squared over n cubed. Now we have to take advantage of those reduction formulas. The sum of I, that's n times n plus 1 over 2. The sum of I squared, well, that's n plus 1, 2n plus 1 over 6. We'll need to use those, as well as just summing up a constant. Remember, if we take the sum from I equals 1 to n of some constant k, well, this is just n times k, since we add up k n times. So when we compute this sum, we still have the limit as n goes to infinity. The sum of 1 over n, well, the n is not affiliated with this sum, so it's just a constant. It stays along for the ride. 1 over n is a constant, so if we sum up 1 over n times, we'll get n over n, just like this last little reduction formula here. Next, sum up 2i over n squared. Again, the 2 over n squared doesn't really affect anything here. The 2 over n squared is just a constant, so we can pull it out of this sum. Really, the only sum happening going on is with that I. We use the reduction formula. N times n plus 1 over 2. That was the sum of I. Lastly, we'll use that third reduction formula, the sum of I squared. We still have the 1 over n cubed. That doesn't get affected yet, but I squared turns into that n plus 1, 2n plus 1, all over 6. We used all three of these formulas, and now we should just simplify and compute the limit. It looks like n over n is 1. We can cancel out some n's as well here. We can cancel an n over an n squared and a 2 over a 2. It looks like this will just be n plus 1 over n. We can cancel one pair of n's here. And if we distribute this as well, we're going to have an n squared with a 6 on the bottom. If we distribute or FOIL out that numerator, 2n times n gives 2n squareds. We'd have 2n plus another n to make 3n, and then 1 times 1 makes 1. There are multiple ways to solve this limit. I'm just going to continue to break things up. We still need to write limit as n goes to infinity once more, 1. I'm going to split this fraction up. N over n plus 1 over n, that would be n over n is 1 plus 1 over n. If we split this fraction up 3 ways, we would have 2n squared over 6n squared. That would be 1/3. We'd have 3n over 6n squared. That would reduce to 1 over 2n. And then 1 over 6n squared. Now we can really take this limit since it's going to infinity. N goes to infinity. They're all in the denominator. So a number over infinity basically goes to 0. 1 over n goes to 0. 1 over 2n goes to 0. 1 over 6n squared goes to 0. And we're just left with the answer. 1 plus 1 plus 1/3. 3/3 plus 3/3 plus 1/3. This is 7/3. And this is the definite integral, which we described like this. The definite integral from 1 to 2 of the function x squared dx. That was a lot to take in, and if this is your first time, I recommend reviewing this thoroughly. We had to do lots of summation stuff, including those reduction formulas, as well as take a pretty hard limit at infinity, not to mention remembering the definition of the definite integral. This problem is worth your review.
Want more bite-sized lessons? Check out the Wize free trial at wizeprep.com. Oh, and subscribe to our YouTube channel while you're here.